Okay. So, among the 4 families of methods to solve nonlinear optimization problems, now we are going to discuss the 4th, that is Lagrange methods. In a way, this is our old friend, because after studying KKT conditions, the first few problems that we solved were actually by trying to satisfy the KKT conditions, and Lagrange methods essentially do that. They try to attack the problem in the complete space of the primal variables and the Lagrange multipliers together. Okay. And the central point in that exercise is to attack the KKT conditions. Now, earlier also we observed that the number of equations that the KKT conditions give turns out to be exactly the number of unknowns that we need to solve in terms of x lambda mu. Okay. So, for the preliminary discussion of how it works, we will start with this small problem which has only equality constraints and no inequality constraints. So, for this problem, minimize f of x subject to a few equality constraints h of x equal to 0. The Lagrangian will be this f x plus lambda transpose h, and therefore, its gradient will be this, and KKT conditions turn out to be this thing equal to 0 and the constraints back here. That is all there is in the KKT conditions for this problem, right. Now, this thing, whether you write in this complete manner or in this shorthand manner, it is the same thing, because this whole thing is the gradient of the Lagrangian with respect to x only. Okay. In a way, if you try to partially differentiate the Lagrangian with respect to lambda, then essentially you will get this, which is anyway the feasibility condition. Okay. Now, if we try to just solve this system of equations, then you will say, let us try Newton-Raphson method, okay, something like that, Newton's method for equation solving. So, if we try to do that, Newton's method for equation solving to solve these simultaneous equations, n plus m equations in n plus m unknowns, then basically we will work with first order Taylor approximation of these. So, let us conduct that first order Taylor approximation. So, as we conduct the first order Taylor approximation of this, we say that grad L at x lambda, in place of that we try to find the expansion for grad L of x plus change in x and lambda plus change in lambda, that is this. So, at kth iteration, grad L of x k plus d k, which is the change in x, lambda k plus y k, which is the change in lambda. Okay. And that will be the grad L at the reference point, which is this, the old one, plus change due to this one and change due to this one, the two first order changes. Okay. So, the change due to this one will be derivative of this with respect to x evaluated at x k and lambda k into this d k, that is this. And what is the rate of change of grad L with respect to x? That is the Hessian of Lagrangian. Plus, then you will do that for this part. So, then you will say the derivative of grad L with respect to lambda k evaluated at x k lambda k, right, just like this. So, derivative of grad L with respect to lambda k, look at it from here, that is the grad L. So, if you try to differentiate this with respect to lambda, you get this, okay, and that is here into the small change y. So, this is the first order Taylor approximation for grad L at a different point, at a close by point. Okay. So, and this has to be 0, because this is supposed to be satisfied in perpetuity. this is 0, later also it should be 0, therefore, its rate of change, this full change, full first order change should vanish. So, this whole thing equal to 0. Similarly, conduct the first order Taylor approximation of this one. So, then okay, so this one this entire equation you can write in brief notation as this is H k, basically H L k, that is Hessian of the Lagrangian, okay, into d k plus grad H y k is equal to this part minus delta L minus grad L, something that is known. This d k and y k, this is what we would like to determine, right, for the change, for the iteration. Okay. Now, similarly conduct the first order Taylor approximation of this one. You will find that this will turn out to be the current value H at x k, that is this, plus grad H transpose change in x, grad H transpose change in x, that is this, equal to 0. And this equation also you organize, take this known thing on the other side, and then you get grad H transpose d k equal to minus H k. Now, these two equations, if you organize together, you find H k d k plus this is A k transpose, because grad H is typically in our notation, shorthand notation, it is given as A transpose. So, this is A k transpose y k is equal to minus grad L k. On the lower side, you have A d k, A k d k plus 0, that means nothing, is equal to minus H k, fine. So, you could write it like this, or this same equation you could also write like this. The equivalence of these two is actually very obvious. Just I am writing this on the board, this top, see the bottom row block is the same. Here also it is A k d k equal to minus H k, here also it is A k d k is equal to minus H k. The lower row block is same. Let us examine the upper row block. If you write this upper row block separately there, I am just writing it, follow this, H k d k plus A k transpose y k, H k d k plus A k transpose y k is equal to, it says minus grad L k, fine. I am writing this in a little open manner, minus grad f k minus grad H k lambda k, that is the full of grad L, right. So, grad L here you see is grad f plus grad H lambda, and that is here grad f plus grad H lambda. The full thing is negative, because this negative sign here. Okay. And now, this grad H k is essentially A transpose, right. So, write it as A k transpose. Okay. Now, take this A k transpose part on this side, okay, and then this gets a little simplified or put in a different form, whatever it is. So, this negative thing goes as positive. So, A k transpose y k plus lambda k, and lambda k plus y k is going to be the next lambda k, right. So, this is going to be A k transpose lambda k plus 1, and that is simply this. Okay. So, now this appears as the second row block here. Okay. H k d k plus A k transpose lambda k plus 1 is equal to minus grad f k, fine. and the lower block is the same anyway. So, you would notice that this is a typical Newton's step. Hessian times change is equal to minus grad. Okay. So, this is a typical Newton step, and you will also recall that this is precisely the form of the key equation that we were solving in the case of quadratic programming problem. Only thing is that in the quadratic programming problem, this everything was constant, all the coefficients were constant. Now, here they can vary, that is the only difference. That means, these can be considered as constant, as numerical values only for a particular iteration in a sub problem. So, this is indeed the form like the formulation of the QP problem. However, if it is this easy, then why delay it so much? It is not that this easy. There are so many issues. So, let us look at those issues. So, first, how do we organize the full problem? We could organize the full problem as minimize f x subject to equality constraints and inequality constraints. So, basically our idea is to define the QP subproblem in every iteration as minimize the corresponding second order change the way we did in quadratic programming problem, half dk transpose HLK dk plus grad f transpose dk subject to the linearized version of these constraints around this point and the linearized version of these constraints around this point. Okay. So, the linearized versions will be simply like this, and we say that this QP subproblem, quadratic programming subproblem, we solve and get hold of dk and lambda k plus 1 and perhaps mu k plus 1 also, and then update. Okay. So, this would be a perfect recipe for an iteration and go on doing these iterations. So, it is not that simple. Why? Because of several things. One is, first attack is on the way we are doing it. What is the use computing just a KKT point? Because we want a minimum. A KKT point is not necessarily a minimum. Of course, the way a quadratic programming problem is solved through descent steps, you have some idea of going not only to a KKT point, but also to a minimum point genuine. But where in this whole thing are we trying to ensure something called descent? Okay. Earlier, when we used KKT conditions to solve optimization problems, we used to switch that, let us say these constraints are active and others inactive. Okay, no, let us say the other set is active and this is inactive, but now we are not going to do it. Now, we are thinking of a continuous iterative process. So, if it is an iterative process, then in every iteration we need to descend along something. Okay. So, this is one issue. Second issue is that what if the QP subproblem turns out to be infeasible? Suppose if the original problem is feasible, that is, original problem has feasible solution, but through the linearization of the constraints, where we get the constraints now, thereby particularly through the inequality constraints, through the linearization of the inequality constraints, little portions of the otherwise feasible domain become infeasible in the linearized versions. That is quite possible, that often happens, okay, depending upon the shape of the constraint surface and the point around which we are doing this linearization. It may happen that some extra part of the domain gets included or some genuine part gets excluded. Such things happen. If some extra part gets included, then that basically means that we will be, our computational domain will be a little larger than the actual domain. So, there is a little chance that we will get a little wrong solution, to be corrected later in some other iteration when the linearization will be more accurate, fine. But if some part of the genuine domain gets excluded, then it might happen that 3 such segments get excluded from 3 sides. As a result, in between whatever little part of the domain was actually there gets lost completely, and that will be dangerous, because then this Q p sub problem will end up at a deadlock that it has no feasible domain, and that will be a disaster, because the actual problem does have a feasible domain, but our step is not allowing it. So, it is like that South Indian joke of saying that even if the god wants to give you something, it is the priest who in the middle does not allow. Okay. So, that is trouble, and we have to safeguard against that. The third issue is that, well, you intend to calculate the Hessian here, and that also not the Hessian of the objective function only, for which we were lazy enough even in the unconstrained optimization problem, where there were no constraints, and now there are constraints. So, here it is not the Hessian of the objective function, but Hessian of the Lagrangian, which means Hessians of so many things. Hessians means second order derivatives, too many second order derivative evaluation you are talking about. So, evaluating Hessian, that also not of objective function f, but Lagrangian, and then after spending a lot of computational trouble, computational cost, if you end up evaluating the Hessian, which is exact Hessian, what if it is indefinite? So, Newton's step issues will start showing up, and then you are again in the old problem. So, this is also a big issue that you have to handle. So, in the remaining part of this discussion, we try to see how we handle these issues together, and the framework that we will develop by that is popularly known as sequential quadratic programming, and that is one of the best known methods to solve this kind of nonlinear optimization problems. The other competitor that it has is the augmented Lagrangian method that we discussed in the previous lecture, and these two methods, both of them are fully general and known to be fully effective. Okay. So, first of all, a so called merit function is introduced. Merit function for any nonlinear optimization problem is a function to measure the merit of a step in the context of a given nonlinear programming problem. Okay. Typical examples of merit functions which people use are these. Basically, this and this are the same thing, quadratic merit function. Here square half is just to ensure that when the square is differentiated, you get this cancelled. Okay. So, half of the grad L square plus half of the constraint violation squares. Okay. So, this set is the total of the violation of the equality constraints, and this is same thing for inequality constraints. So, and this is the case where inequality constraints are not there. Okay. Another possibility of a merit function is this, which has a penalty term, where this has been included by a mod function and a penalty. So, this is actually linear and non differentiable. So, that is an issue, that can be an issue. Okay. Now, this is one thing that we keep a merit function in hand, which we will use somewhere for line search purpose. And you would notice that a descent in the merit function would basically mean an improvement in the satisfaction of KKT conditions only, because KKT conditions ask for this to be 0 and this to be 0 and this to be 0, right. This is the max function. Okay. So, max of 0 and g. So, these 3 zeros mean this is the gradient condition from KKT, and these 2 are together feasibility conditions. Okay. Similar thing here also. Okay. Now, so this will mean a combination of improvement in the function value. See here, that is more apparent, here f x itself is sitting. Okay. So, improvement in the function value and an improvement in feasibility. A combination of those two is basically represented in the merit function. So, basically this shows the merit of a particular proposed descent step. Okay. So, Taylor approximation and global minimum of this merit function turns out to be this. So, at this wherever this is satisfied, typically the merit function goes lowest. So, this is what it means. Descent of merit function is combination of descent of the function and reduction of constraint violation. However, do not think of this as the new objective function, it is not. Okay. So, that will not make very good sense. Okay. What else we do? We say that we are obliged to improve the feasibility of the approximated QP subproblem. Okay. So, we want to ensure that. So, allow it a little long rope. So, the way you allow the long rope is by telling that the linearized version of the inequality constraint function now does not have to be less than equal to 0. We will be okay if it is less than equal to some positive number, okay, some positive number. And then say that how big that positive number can go, we do not know, but try to ensure that it does not go very large. How do you ensure that? You can say that whatever you are trying to minimize, with that you add a penalty term involving these loose extra rope thing. Okay. So, that means that you enhance the domain as much as you need, but do not take more than you need, because there is a little penalty for that, there is a little cost for that. Okay. So, only that much extra space you try to claim, which becomes necessary for you. So, this is how you put it. So, a few extra variables come into picture, okay, which are these. So, now other than x, you have got these also as additional variables of this sub problem, this quadratic programming sub problem. Okay. So, this is another thing that we have to ensure. And third, Hessian, do not calculate, okay, update. And we know we are quite habituated of updating Hessian matrices because of the Quasi-Newton method background that we have developed, and how to find out the step length. So, for that use line search as usual. Okay. So, typical Quasi-Newton steps, which we have been using since unconstrained optimization problems, we will use such line searches, and based on the change in the function value and change in the variable value, we will make updates on the Hessian, as we used to do in unconstrained optimization problem. Okay. However, there is one issue here. In Quasi-Newton update, guarantee of continued positive definiteness depended on this Pk transpose Qk being positive, which is true for an exact line search, which also means complete line search. We discussed earlier that in this Quasi-Newton update, if we conduct inexact line search, then this will suffer to some extent, and that was one issue in inexact line search in Quasi-Newton methods. And now we will be actually forced to if either do inexact line search or cut short the line search extent because of reasons of feasibility, because now there are constraints. So, wherever the exact line search takes us, that point may not be feasible. So, we may have to cut short our line search, not because of the minimum appearing on the way, but because of the constraint boundary appearing on the way, and that is one issue which we have to keep in mind. Okay. And therefore, the BFGS update, the standard BFGS update is in this case, in this constraint optimization case, is a little modified. Hk plus 1, that is new Hessian, is equal to old Hessian plus this. This was the formula with Qk here in the case of the original Quasi-Newton BFGS update, unconstrained optimization update for exact line search. Now, we say that we are putting Rk here, and what is the difference between Rk and Qk? Here also it is Rk. Okay. What will be the difference between Rk and Qk? So, Rk is this. Now, try to see, if you put theta k equal to 1, then Rk equal to Qk plus 0. So, in that case Rk equal to Qk. That means, if you put theta k here as 1, then you will get the full fledged proper BFGS update. Okay. And the modification now is that you put 1 here, that means you put the standard BFGS update only if this guy has a margin from 0, that is, it is larger than this. Otherwise, put this. Okay. So, here you see such a complicated thing below. So, this is the way you make the modification, and people have found that typical values of gamma to be used here is something like 0.2, 0.25 kind of thing, with which it is found to behave well and work satisfactorily. You can analyze and find out to what extent that is true and why and so on, but this is what people who have conducted a lot of research on a lot of number of cases have prescribed. Okay. So, with this modification you can use BFGS update for Hessian updates. Okay. Now, with all these modifications put in place, the complete algorithm that you develop is called the algorithm of sequential quadratic programming. Okay. So, this does a sequence of quadratic programming subproblems, okay, and on the way a lot of other paraphernalia to handle this issue and that issue. Okay. So, for minimizing this function with subject to these equality and inequality constraints, the full algorithm starts with a selected starting point and initial values of Lagrange multipliers taken as 0, initial Hessian estimate taken as identity, and iteration starts. From here the iteration starts. Solve this QP subproblem in this iteration, the one that we formulated. Okay. From the result, collect dk and lambda k plus 1. If dk is 0, that is in the iteration in which dk becomes 0, stop. Typical iteration will have dk non-zero, that is a reasonable large size vector. Now, this 0, of course, you understand that you have to compare not as 0, but its magnitude being extremely small and such things. Okay. So, along dk you conduct a line search on your chosen merit function, say this one or this one, whatever you choose as merit function. As a result, from xk you reach xk plus 1. Okay. Along this dk direction you have moved from xk, and then conduct the update. Xk plus 1 update you have already made, and now make the Hessian update. This where Rk is this, using theta k 1 or this thing depending upon what is the value of this. Okay. And then go to the next iteration, and this is the sequence. Okay. So, this is known as the sequential quadratic programming, and perhaps the most popular and most well known nonlinear optimization method. I mean, most popular, well known and efficient, okay? Because there are other methods which are more well known, more popular, but not so efficient. Okay. So, and I have personally found augmented Lagrangian method more appealing, and some of our implementations in non-trivial serious research problems are on augmented Lagrangian methods. But I do not know why augmented Lagrangian method has not been found so much favor among the developers of the library routines. For example, MATLAB library routine has been developed on this sequential quadratic programming. Okay. But I have found augmented Lagrangian method equally general, equally effective, and in our in the hands of our group, augmented Lagrangian method has performed really well. Quite a few of my students have used it. Okay. So, here we complete the nonlinear optimization general families of methods, because today is the fourth family that we discussed. So, these 4 families we have discussed, and now we are left with those little outside topics which form an anchor in our mainstream discussion of the course. The mainstream discussion is over at this point. Okay. Thank you.